Welcome to the Deep Dive, where we take your fascinating finds and really extract the crucial insights.
Yeah.
Today, we're diving into a project you flagged for us. It's using some, well, incredibly smart AI to tackle a surprisingly high-stakes problem, identifying pills.
Exactly. You sent us this report, Pill Identification Using Google Gen AI.
Yeah.
It's from a Google Gen AI capstone project by James Hahn and Alex Hui.
Right.
And it really got us thinking about, a challenge we probably all just take for granted.
Totally. Misidentified medication, it sounds mundane,
Yeah.
but the risks are actually pretty significant.
They're sure.
And the usual ways of doing it, well, they're not foolproof.
Not at all.
So our mission today, really inspired by your contribution, is to understand how this cutting-edge generative AI can automate this whole process.
Okay, so let's unpack the core problem they're tackling here. It's pretty straightforward.
Yeah.
How do we accurately identify pharmaceutical pills just from a picture using Gen AI?
And it's not just about convenience, is it? Your report points out there are real dangers with lookalike medications.
Oh, absolutely. You can just imagine the potential for mix-ups in a busy pharmacy, even at home. Scary stuff.
Definitely.
So the ultimate goal here is a system that can automatically look at a picture of a pill and pull out key structured information. Things like its form, tablet, capsule, whatever.
Shape, color.
Or colors, yeah. If it has markings, an imprint.
Yeah.
If it's got a score line, for splitting.
Right.
And getting that structured data, that's what makes safer medication use possible. It reduces those errors.
So the report isn't just asking, can AI do this, but specifically how? How do we build an automated system with generative AI and these retrieval-augmented techniques?
Like ADVIG. We'll get into that.
And there's a big assumption baked in right from the start, isn't there?
A huge one. They assume we have a complete, totally accurate database of all known pills. That's foundational.
Which leads us straight to the key assumptions underpinning the whole solution.
Yep. Yeah. Number one, as you said, the NIH ePIL-I database, which they use, is assumed to be comprehensive and correct. Every pill is in there, perfectly described.
Makes sense. If the library is incomplete, the AI is flying blind.
Exactly. What else are they assuming? Image quality. That's critical.
Ah, right. Garbage in, garbage out.
Pretty much. The system assumes the images you feed it are good enough, in focus.
The whole pill visible.
The pill clearly visible, not half hidden by fingers or something. A blurry shot, forget it. That makes it tough for anyone, human or AI.
Yeah, like trying to ID a car from just a blurry taillight.
Exactly. And the report also assumes the AI model can access this whole database and search the web.
Okay, the database access makes sense, but why the web search?
It's like a backup, or for extra context. It lets the AI pull in more details, maybe verify things, beyond just what's coded in the database. Another core assumption. The way they've defined how to describe a pill. The attributes, like form, tablet, capsule, other. The imprint details, score lines, they assume that set of characteristics is enough to uniquely identify every single pill out there.
So the description format itself has to be really robust and detailed. No ambiguity allowed if you want accuracy.
Precisely. That structured approach is vital. And the last key assumption.
What
They assume a controlled environment, what they call non-adversarial.
No.
Meaning it's not expecting people to actively try and trick it, feeding it deliberately misleading images or altered pictures. It's designed for, say, a pharmacist using it properly, not someone trying to fool the system.
Okay, right. That makes sense for this kind of application. So we've got the problem, the assumptions. Let's get into the solution itself. The report lays out this end-to-end pipeline. Where does it start?
It kicks off with data acquisition. Step one is just getting that NIH ePIL-ID data set, downloading it, getting it ready. Like we said, the whole thing relies on this data being good.
Then comes schema definition. This sounds like setting up the rule book for the AI.
That's a great way to put it. The report really emphasizes setting up a strict JSON schema.
JSON, okay.
Yeah, for all those pill attributes we mentioned, form, shape, color, imprint, scoreline, all of it, this forces the AI's output into a consistent, predictable format.
Which is crucial for actually using the results, right?
Absolutely. For example, form has to be tablet, capsule, or other. Color needs to be a list because pills can have multiple colors. It specifies how to describe imprints and score lines too. Very structured.
Got it. Next up is AI integration. How does the AI actually look at the image and figure things out?
Okay, this is where Google's generative AI comes into play. They mention using few-shot prompting.
Which is like giving it a few examples to learn from.
Exactly. You show it a few examples of what you want. And they also apply constraints, so the output has to match that JSON schema they defined. It guides the AI.
Okay, so it's not just guessing wildly, it's directed.
Right. And then we get to retrieval augmented generation, RAG.
Yeah, that term. What's the core idea there?
Think of like the AI cross-referencing. It takes the image you want to identify and all the pill info in the database and turns them into these numerical fingerprints, embeddings.
Okay, mathematical representations.
Sort of. Polls with similar features end up having fingerprints that are mathematically close. Then, using a special vector search database, they use ChromaDB, here, the system can super quickly find the pills in the database that are most similar based on those fingerprints.
Ah, so it finds the closest matches in its library.
Exactly. It helps ground the AI's identification in the actual known data. It's not just relying on the model's internal knowledge alone.
So it's comparing the new picture to this huge library. Makes sense. The report also mentions an agentic workflow. What's that about?
This is basically the conductor of the orchestra. It orchestrates all the steps we've discussed. It's not just one step.
Right.
The agent manages the sequence. First, analyze the image, then retrieve similar examples from the database, then use all that info to make a reasoned identification.
And reasoned is important, right? We want the why.
Definitely. Explainability, and the final output from all this.
What does the user get?
The goal is a structured ID. All those attributes from the schema clearly listed. And importantly, it should be explainable, often including a link or reference back to the actual entry in the NIH EPLEAD database.
Oh, that's useful. So you can click through and see the official info.
Exactly. Full transparency.
Okay, so that's the blueprint, but the report you shared actually shows some of this in action, like in a coding notebook.
Yes, exactly. It gives a peek into a Kaggle notebook where they implemented parts of this. It even starts with some practical housekeeping,
Like what?
mentioning they had to run pip uninstall for certain packages like KFP, Jupyter Lab,
Yeah.
things that could conflict in the Kaggle environment. Just shows the real-world setup stuff.
Yeah, it's never just plug and play, is it? There's always some setup.
Rarely. Then the notebook shows downloading and extracting that NIH EPLE dataset straight from GitHub. That's step one, getting the raw data.
And then connecting to the Google AI.
Yeah. It details setting up the Google GenAI client, installing the necessary libraries Google GenAI, Google API-Core. These are the software bits that let their code talk to the Google AI models.
And the prompt, how they tell the AI what to do.
Right, the prompt. It's basically the instruction set. Very clear. Describe the pill in the image based on form, shape, color, imprints, score lines. Describe those features. The goal is extracting that structured info.
And enforcing that structure using the schema definition.
Yes, exactly. The image description schema is shown, defined in that JSON format, lists all the properties, specifies the data types like color being a list of strings, super important for consistency.
Okay. And the vector database part, ChromaDB, how's that shown?
The notebook shows creating a ChromaDB collection. That's where the embeddings, the fingerprints get stored. It also defines key functions, upsert and query.
Upsert to add data, query to search.
You got it. Upsert adds the embeddings and the pills metadata to the database. Query is how you search it later to find similar pills.
And they actually load some images into it.
Yeah, as a proof of concept, they index 50 images from the dataset.
Okay, just a sample.
Right. It involved getting the NDC, the National Drug Code, that unique ID from the file name, converting the image data to text using base64 encoding, getting the structured description from the AI using the schema, creating the embedding of that description, and then upserting all of that into ChromaDB.
Wow, okay, that's quite a few steps just to get one image indexed properly.
It is. It's methodical. You need the image, its description, its embedding, and its metadata all linked up correctly in the database.
And did they check if it worked?
They did a quick sanity check. They queried the database using one of the images they just indexed, and the output showed the correct JSON description, colors, form, shape, etc.
Good. So the retrieval part seems functional. Then the report talks about grounding using Google Search. How does that fit in?
This adds another layer. Confidence. Detail. The prompt they use for Google Search gives the AI examples of how to format the search results. It asks specifically for the medication name, dosage form, a brief description of its use, using the NDC number to search.
Ah, using that unique drug code.
Exactly. And they show an example with Stratera.
Okay, what happens there?
They feed the system the NDC for Stratera.
Right.
It uses Google Search, finds the brand name, the generic name, atomoxetine hydrochloride, confirms it's a capsule, says it's used for ADHD.
Wow.
and even gives the source URLs where it found the info. So it's not just identifying, it's doing a quick, verifiable background check online.
That's really useful. Not just looks like this, but here's verified info about it.
Exactly. It adds a lot of value.
And finally, this pill identification bot they built. Tell us about that.
Right. The bot. It's basically a Gen AI agent that pulls all these pieces together.
The conductor again?
Kind of. It uses tools like describe image for the analysis, retrieve pill from NDB for the vector search, and search web for that Google grounding. It runs on Google's Gemini 2.0 Flash model and uses frameworks like LangChain and LangGraph to manage how these tools talk to each other and in what order. Think of it as a specialized assistant for identifying pills.
So it integrates everything into an interactive system. What's its main job, according to the prompt?
The system prompt tells the chatbot its goal is accurate identification and providing useful info, but concisely. Describe the pill, find the NDC, search the web for details. Don't be too chatty.
Does it remember the conversation?
Yes, they use a conversation state class. So it keeps track of the messages, allowing for a more natural back and forth. You don't have to repeat yourself.
And the tools it uses, like describe image, how are they set up?
Well, get capabilities is simple, stateless. But describe image is stateful. It takes the image file path, uses the Google Gen AI client to get the description based on the image and the schema. And there's a similar helper function for the web search using the NDC.
And LangGraph ties these tools together.
Precisely. The notebook defines the agent tools, then uses LangGraph to create nodes, including a special processing node for stateful tools and edges, the connections between them. It maps out the conversation flow and the AI's actions.
Like a flow chart for the conversation.
Yeah, a dynamic one. And they show it working.
With a test image.
Yep. They copy a test.jpg file, user types. Describe test.jpg for me.
And the bot says?
Something like an orange oblong capsule with no scoreline or imprint. Just the description.
Okay.
But then the user asks for more. Describe test.jpg, look up its NDC, and search the web for additional information on this medication.
The full request.
Right. So the bot goes through the whole workflow, describes it, tries to find a match in its NDC in the database, then uses that NDC to search the web.
And the final output for that example?
It identifies Strattera, gives the generic name, the NDC, confirms it's a capsule, mentions its use for ADHD, and lists the source websites. It really shows all the parts clicking together. It's like building this little detective for pills.
That's a fantastic example. It really demonstrates how these different AI components can collaborate seamlessly. Okay, so stepping back, what are the big implications here? What does a system like this mean?
Well, the report makes a strong point. If you have that complete and accurate database,
The big if.
then this system has the potential for really reliable, unique pill identification. Think about reducing medication errors, maybe preventing hospital readmissions from those errors.
Which is a huge cost, both financially and in human terms.
Exactly. This tech, if it's accurate and widely adopted, could make a real dent in that problem.
The real-world impact could be pretty substantial then.
Absolutely. Faster, more reliable access to critical medication info that directly improves patient safety in pharmacies, hospitals, maybe even apps for home use.
You could imagine integrations too, right? Checking against patient records for interaction.
Oh, for sure. That's where it gets really powerful. Flagging potential issues based on the pill you just identified, that's transformative potential right there.
Okay, so let's recap this deep dive. Thanks to the report you sent in, we've explored a really innovative use of generative AI, RA, agentic workflows, all focused on automating pill identification from images, something often prone to human error.
And the promise is significant. Better accuracy, improved safety in how we use medications.
And it's a big but we keep coming back to.
It hinges on that database. As the report stresses, the cornerstone is the completeness and accuracy of that reference data. Without that solid foundation,
The AI is limited.
severely limited. And just from experience, building and maintaining a truly comprehensive, always up-to-date database like that, that's a massive challenge in itself.
That's a really vital reality check. So as we wrap up, here's a final thought for you, our listeners. Considering how fast AI is moving, what other everyday tasks that rely heavily on human accuracy right now and are prone to error, what else could be revolutionized by this kind of tech?
It's a fascinating question. And hey, if you want to dig into the data source itself, the report mentions the original Apellidy dataset paper by Usuyama and colleagues from 2020. Worth a look if you're curious.
Great pointer. Thanks so much for joining us for this deep dive. If you have more intriguing questions or topics you think we should explore, please send them our way. Until next time.